Thanks, Elisa, for the introduction. Thanks to Kevin, Idris, and Elisa for having organized this workshop and in this Christmas period, and for having invited me. So today I'm going to talk about a topic in shape optimization that I'm sure many of you have already heard about. However, in the first part of my talk, I will recall what is the setting of the problem and what are the main questions. So I will give the general picture. And then in the second part, I will focus my attention on an explicit example. Okay, what is the setting of the problem? The first ingredient is a triple of shape functionals that here I denote by F1, F2, and F3. They are defined in a class of admissible shapes, calligraphic A, which encodes all the geometrical and topological constraints that you have in mind. So you can prescribe convexity, simple connectedness, closeness, openness, whatever. Everything is encoded by the class A. Then the Blaschke-Santaló diagram associated to this triple of shape functionals is the following set, denoted by calligraphic D. It is a subset of the plane. Its points are pairs xy, which have the following property. There exists an admissible shape such that when you compute f1 at this shape, you find x. When you compute f2, you find y, and f3 is equal to 1. Okay, so in other words, it is the range in R2 of the vector shape functional f1, f2 when you prescribe f3 as a constraint. Okay, so you measure, you look at the range of this vector shape function. You take a shape, you compute f1 and f2, you find a point in the plane, and you take the collection of all these points. So the constraint f3 is quite annoying, but in many cases it can be removed in the following sense. If your shape functionals fi are homogeneous, alpha, beta, and gamma homogeneous, then the constraint f3 can be enclosed into the shape functional as follows. So the diagram turns out to be the same diagram associated to this pair, which is f1 times f3 to a suitable power, f2 times f3 to a suitable power. And the advantage is now that you don't have to care about f3. The other advantage is that the two components here, which from now on I will denote by capital X of omega and capital Y of omega, are now scale invariant. This is an advantage because when you compute this pair of shape functionals on any homothetic set, you find the same value. For example, any ball in the space with any radius is associated to the same point of the diagram. Okay, so the goal of this kind of problem is to describe this set. So given A, sorry, here it should be capital X and capital Y, try to detect what are the points described by this diagram. Let me summarize what are the main questions that one faces. The diagram is unknown. The first natural question is the diagram bounded? Or can we find shapes which make capital X and capital Y arbitrarily far from the origin? So can we obtain arbitrarily large values or not? Then what about the topology? So is the diagram closed? Are there holes? And what can we say about the boundary? What are the optimal shapes if they exist sitting on the boundary, so associated to boundary points? And if, as in this case, we have a corner, well, what is the behavior of the diagram near the corner? This is a picture that will come in the end. Okay, so let me give a couple of motivations. First of all, give a complete description of the diagram is equivalent to characterize completely the relation between the shape functional capital X and the shape functional capital Y. To explain this, let me make an example. If assume that you have found that the diagram is this set here, then it means that the shape functional capital Y, omega, is between this lower function small f, which describes the graph here, computed at capital X of omega, and as the upper bound you have G computed at capital X of omega. and the two bounds in this picture are optimal. Another motivation, possible motivation, is the following. So assume that you have completely described the diagram. So you have made an effort for describe. So it is difficult, but once you have done this effort, now something is easier. So if you have to optimize another function f on the class of admissible sets, if it is of the form small phi of x and y, then optimizing f over the class of admissible sets turns out to be equivalent to optimize a function of two variables, so phi, which can be complicated. However, it is a function of R2 defined over a known set. Let me conclude the first part with some literature. The first contribution is probably due to Blaschke in 1916, who adopted this approach to describe the relation among 3D convex bodies of the integral, the surface integral of the mean curvature, the surface area, and the volume. Then 50 years later, this approach has been followed systematically by Blaschke to describe the relationship between geometric quantities for 2D convex bodies. And then many other authors have used this approach. Here I give a couple of examples of geometric type shape functionals. So you have the minimal width, the radius, the diameter, the integral on the boundary of the curvature, and so on. So there are many, many examples in the literature. Another class of examples available are of a spectral type, in which usually one takes as constraint, so the F3 of the beginning, the volume, and then one wants to understand the relation between, for example, the first two Dirichlet eigenvalues or Neumann eigenvalues, or first Dirichlet eigenvalue and torsional rigidity, or first Dirichlet eigenvalue perimeter. So let me just mention that these papers here, which are more recent with respect to the other ones, were somehow inspiring for what I'm going to talk about, because many of the ideas, many techniques are borrowed from this. Okay, let me now pass to present an explicit example. We consider three shape functionals, P, W, A. P will be the perimeter, W will be the moment of inertia, and A will be the area in R2. Everything that I will say is work in collaboration with Raphael Gastaldello, who was a student of mine in École des Mines in Nancy in France, and Antoine Henrot, who is in Nancy. So the perimeter and the area, I don't have to recall what they are. Let's be more precise about the functional W. We are in R2. W, or better WG, denotes the moment of inertia with respect to the center of gravity. So it is defined as the integral over omega of the square distance of points of omega to the center of gravity. So here xg and yg are the coordinates of the center of gravity. Note that here there is a hidden difficulty in the sense that when you want to deal with this functional here as a shape functional, you have to notice that when you move and you perturb a little bit omega, you have this shape here which changes, but also the center of gravity changes too. So considering this as shape functional has an extra difficulty. You have to take care about the integration set and the center of gravity. So as a first step in the study, we decided to remove this difficulty. How? By adding an assumption on the domain. So we work in a very particular and easy class of domains, which are convex sets, which have two orthogonal axes of symmetry. When you have two orthogonal axes of symmetry, then the center of gravity is in the intersection of these two axes. So if we decide to, up to a rotation and translation, to put all our shapes with two orthogonal axes of symmetry coinciding with the coordinate axis, then the center of gravity is always the origin. So our shape functional here becomes simpler. It is nothing but the integral of x squared plus y squared over the shape. Okay, let me make a picture. our sets are of this form. They have two orthogonal axes of symmetry. They are convex. And in some sense, what we do when we compute things is that we consider only this green part. So because the other parts are the same, so all the three shape functionals can be computed by multiplying by 4 what happens in this first quadrant. And something that is also useful in the proofs is that this shape can be described by this function here, which describes the boundary. The boundary here is the graph of a concave function. Okay, so let me specify what is the diagram. There are many ways of putting together perimeter, area, and moment of inertia. We decided to mix them in this way. We have a constant, multiplicative constant, which is a normalization constant. I will talk about this in the next slide. Then as first component, we take the square of the area divided by the moment of inertia. And in the second component, we have the area divided by the perimeter square. And as I said, we work among 2D convex bodies which have two axes of symmetry. So I will refer to the first component xx, the second as y. But since they are not easy to be memorized, I will recall the definition in every slide. So, just a remark, as I said, the two components are scale invariant. And this is important because, as I said before, we can not care about the homothetic copies of a set, but also because we can actually assume that all our shapes are contained in a fixed box. Because you take a shape, you rescale it till it fits a given box, and you compute the shape functionals. And you get the same value of x and y. This is useful because now the diagram is the same of the diagram associated to the two components when we add the inclusion in a fixed box. This is important because it gives somehow a compactness of the shapes under study. Okay, so the first step that one does is to look for first properties, is to study separately the functionals x and y. So if you study only the functional constant times a square, area to the power 2 divided by w, well, of course, you notice that it is positive, everything is positive. It is never 0 because we are taking convex bodies, so they are a convex set with non-empty interior, and it is bounded by 1. This bound can be obtained, for example, by describing the shape in polar coordinates, and the value 1 is attained only at disks. So you have equality only at any disk. So the reason of this prefactor is to have here the optimal constant to be 1. Moreover, all the shape functionals under study are continuous with respect to the Hausdorff convergence, and so you find that capital X is continuous. The same can be done for the other coordinate. You look for lower bounds and upper bounds of 4 pi times the area divided by the perimeter square. Well, the lower bound is again 0, and the upper bound is given by the isoperimetric inequality, so you have that maximizers are disks, and the value is 1. Once again, this functional is continuous. Let me give a picture of what we can deduce from this. First of all, our diagram, whatever it is contained into the square 0, 1 times 0, 1. Moreover, the diagram doesn't touch the boundary of the square except at this vertex 1, 1, which is associated to all the possible disks. Moreover, I didn't say that the threshold 0 can be attained asymptotically by taking thin domains. So you take any admissible set with two orthogonal axes of symmetry, you start to collapse it either to the horizontal axis or to the vertical axis, and you end up with 0 for both coordinates. So it means that if you follow this kind of trajectory, so if you take a set and you compute the value of x and y, you draw a trajectory which goes to the origin. The origin is not included in the diagram, however, it is in the closure. More precisely, one can prove that the closure of the diagram is the diagram itself plus the origin. The last property that I give concerns admissible shapes. So, admissible shapes are recalled are convex set with this symmetry property. When you pick any pair, omega 0 and omega 1 of shapes with this property, and you take the Minkowski sum multiplied by some constants, by any constant, you stay in the class. Moreover, if you look at this element of the class as a function of a parameter t, which varies in 0, 1, so you take a sort of convex combination, convex Minkowski sum, you obtain a continuous curve in A. So given two shapes, you are connecting them with a continuous path in the class of shapes. Then you can apply x and y, our shape functionals, to this family. And what you find is, in view of the continuity that we have proved, you find a continuous path in the diagram. So it means that you can connect any pair of points in the diagram by a continuous curve. So this means that the diagram is connected by arcs, so it is connected. This is the very first thing that one notices, very easy properties. Let me now pass to some harder properties. So the first thing, so the second thing that one does is to look to better upper and lower bounds. So we said that the diagram is contained in a box, 0, 1 squared, but can we be more precise? And this question can be addressed as follows. You fix an admissible point between 0 and 1. And then you ask yourself, well, what are the possible coordinates y which have this fixed x? If the diagram is like that, you have that the supremum should be this point, the infimum should be this point. Maybe they do not belong to the diagram. These two values, we define them as L minus of x and L plus of x. So they are the infimum and supremum of the y coordinate obtained, computed, and admissible sets which have a given coordinate capital X, small x. In other words, if you want to minimize and maximize the perimeter when the area and W are fixed. This is equivalent. Okay, so it is not hard to prove that actually this infimum and supremum are minimum and maximum respectively, because you have continuity, enough compactness, nothing collapses. And therefore it means that on these points here, there are shapes. So they are in the diagram, they are associated to real shapes. We don't know about this part in the interior, but the upper and lower points here are associated to shapes. What about regularity? This function here, by definition, it is easy to prove that it is lower semi-continuous. The L plus is upper semi-continuous, but from the definition, we do not have directly continuity. What could happen is the following. For the upper boundary, let's say, it could happen that it does something like that. So it means that L plus, which is upper semi-continuous, has some vertical jump. So the graph follows the boundary, then you have a vertical jump, then you continue with the boundary, then you have another vertical jump, and so on. And the same for the lower boundary. It could, the function L minus could display jumps like that. Well, what we prove is that this does not occur, and the two functions are actually continuous and increasing. Moreover, and here is the main, let's say the main result, the diagram is completely described, completely in some sense, by the two functions L minus and L plus. So it is the region between these two functions, which go from 0 to 1. Both of them go to 0 from 1 in an increasing way. In particular, the diagram is simply connected. So this is a satisfactory result, but not completely, because one should exactly describe what are L minus and L plus. So what is the function of small x explicitly? And this is something that we don't know. So we have partial results. The next slides, I will focus my attention on a part of the proof of the continuity for L plus and the increasing property for L plus. The same strategy can be applied to the lower boundary L minus. And about the simple connectedness, this is done by adapting an argument by Ilias and Jimmy Lambolet on another Blaschke-Santaló diagram. Okay, so keep in mind that I want to study L plus. So I want to study somehow the optimization of area divided by perimeter to the power 2 when area to the power 2 divided by W is fixed. The first ingredient is to detect what are the optimal shapes associated to boundary points. Because we need to do a final analysis in these kind of points to show that we don't have jumps here and there, and therefore it is useful to have an information on the optimal shapes sitting there. And this is done by applying an argument by Jimmy and Roots and Pierre, but also is contained in many other papers by Jimmy, which allows to characterize the regularity of optimal shapes among a convex set in a certain setting. With these arguments, we can obtain that the optimal shapes for the upper part are C11, whereas the optimal shapes in the lower boundary are polygons. Let me make a picture. So we have the disk here on the upper part, so in the graph of L plus, we have C11 shapes. And on the graph of L minus, we have polygons. So this makes our study much easier. And another remark is that the two curves cannot intersect. So the two graphs cannot intersect because we don't have C11 shapes and polygons do not have common shapes. Okay, so keep in mind that L plus is associated to C11 shapes. How do we prove the continuity of L plus? So as I said before, we need to prevent this situation. We put ourselves to a point of associated, so a point of the graph of L plus, which is associated to a C11 shape omega. As I said, it could happen that here we have a jump like that or a jump like that. To prevent this situation, it is enough to show that given omega, C11, we can deform it a little bit in a continuous way, in such a way that the coordinate x increases or decreases. See, if we are able to make x increase, this cannot happen because we should go, well, in any direction, however, x increases, and this is not possible. And if you are able to make the coordinate x decrease, here is this is prevented. What is enough to do is to construct this deformation by means of a deformation field V, which acts in the following way. So we want to focus ourselves on a strictly convex part of the boundary, and C11 shapes have a strictly, at least a small part which is strictly convex. And if we if we take a deformation field V, so we deform the shape, the boundary, and the shape according to this direction or its opposite, we stay in the class of admissible shapes because convexity is preserved. Then we do the same deformation in all the symmetric parts, so we preserve also symmetry. So we can go in both directions. If it happens that the shape derivative of the functional capital X along this direction is different from 0, then by following the deformation according to V or the opposite deformation, we increase or decrease the functional capital X. So it is enough to find such a deformation. Let me recall that X is this function. So in some sense here, we are dealing only with one shape functional, not with the vertical one. It is only the horizontal one. And this is proved by contradiction. So assume that this is not true, then it means that for every deformation field which is concentrated on the strictly convex part, the derivative is 0. Then you use the fact that X has an explicit expression, you know what is the shape derivative of the area, you know what is the shape derivative of W, because W is nothing but an integral of a function over the shape, so the shape derivative of W is the integral on the boundary of x squared plus y squared multiplied by V dot n. So it is standard calculation. And imposing this to be 0, we find that this integral has to be 0. Okay? But this has to be 0 for every deformation field V. So using the arbitrariness of V, we find that this integrand here has to be 0. Since this is a constant and this is a constant, it means that the norm of the points of the boundary gamma plus have to be constant. So in other words, okay, this norm of x squared has to be 2w divided by a to make this 0, and therefore it means that the strictly convex parts are contained into the boundary of the disk with a given radius, but not only. This disk, so these parts are associated to a circle centered at the origin. So now you think a little bit about what this means. So you have portions of a circle, and then you can have flat parts. Well, the only way to have this staying C11 is that our shape is the disk. Well, I didn't say before that we are interested in doing that except for the disk, because for the disk, everything, it is easier. Because we cannot go on the right of the disk, we can go left, but this is easy to be prevented. So it is enough to do all that for shapes different from the disk. And so we find that if a shape is different from a disk, this cannot occur, so this is always verified. And this proves the continuity. The same kind of strategy, so using shape derivatives and argue by contradiction, can be used for the proof of increasing character of L+. So by contradiction, what happens if the upper curve is not increasing? So it means that at some point it decreases. It means that there is a point here in the graph associated to a shape, C11 shape, different from the disk, which is a local maximizer of the shape functional y, the vertical one. So to prove that this cannot happen, it is enough to prove that for a C11 shape, which is this one, different from the disk, we can find a deformation field which is, as before, concentrated on strictly convex part, for which the shape derivative of this vertical component is different from 0. If you are able to do that, then up to taking v or minus v as deformation, we can increase the value of y. So we can deform this shape, and the continuous deformation makes us draw a continuous trajectory which starts here and goes somehow up. And this cannot happen if it has a local maximizer. So once again, we prove this light blue lemma by contradiction. Assume that this is not the case. So assume that we have a C11 shape different from the disk for which the shape derivative is always 0. Then we use the formula of shape derivatives in this very simple case. We know the shape derivative of the perimeter, it involves the curvature, and we find this optimality condition. The curvature is constant on strictly convex part and is given by this perimeter divided by twice the area. In other words, as before, the strictly convex part is made of arcs of circle. All these arcs have the same radius, which is this one, but this time they are not constrained to have the same center. These arcs can be associated to circles centered anywhere. So imagine, for example, a stadium has this property. You have two arcs of circles, then you have flat parts. These two arcs of circles have the same radius, but their centers do not coincide. Let us look at more closely at what can be this shape with this property. So we take one arc of circle, one boundary arc, so it has a given radius. Let us take it maximal, in the sense that after that we have two segments, two flat parts. And notice that if we join the center of the arc with this junction point, we have, of course, two segments with length, the radius, and which arrive orthogonally to this flat part. And then we go on, so we take a maximal segment, we draw an arc, till we complete the picture, and we find something like that. In other words, we see that the shape omega is made by a convex polygon capital K. Then we have some rectangles obtained by joining the centers of the circles with the contact points. And then we have portions of this. Well, this has a precise structure. Omega is a Minkowski sum of the convex polygon and of a ball, a disk of radius r. For these kind of shapes, the computation of perimeter and area, which are part of our shape functional y, are explicit. The perimeter is nothing but the perimeter of the polygon plus the perimeter of the disk. The area is the area of the polygon plus the area of the rectangles, which is perimeter of the polygon times r, plus the area of the disk. So everything is explicit. Here we have that k is the unknown, but r is given by this relation. So putting this relation r here, one does a very simple computation, and one arrives that k, the polygon k, the only possibility is that this k is the empty set. So it means that omega, actually, if this k disappears, all the rectangles collapse, and you only have the disk. And this is a contradiction in the sense that it is useless. Okay? So we have proved that for every C11 shape, this non-zero derivative can be found. And therefore, going back to our starting point, the upper boundary has to be increasing. As I said, similar features, similar properties can be proved for the lower boundary. Okay, let me make two final marks. One is related to conjecture bipolar. This is related to future work that we will do. Actually, in the very first steps of our study, what we did is to compute capital X and capital Y to some shapes. So you pick known shapes, you pick a family of shapes, for example, I don't know, ellipses, the disk, or some polygons, and you try to see what are the points in the diagram. So you start to draw some curves, some points which are in the diagram, and we notice that all these points stayed above a line. In other words, the first numerical attempt suggested that the diagram should be in this half plane for some constant c. So our first intuition was that the constant had to be strictly positive, but we were not sure. Maybe in our computation we did not consider points here, so maybe the real line, which is correct, is c equal to 0. C equal to 0 works, but so the question was, what is the maximal c that can be attained? Well, if you work a little bit with what means maximizing capital C, well, it turns out that it is equivalent to maximize the perimeter squared times the area divided by W. It is another shape functional which mixes the two coordinate functionals. Let me denote it by capital F. We maximized it in our class, and we found that an explicit best value, which is the one of any rhombus. So if you take, starting from the square, and you start to shrink it to a segment, you always find that this is constant, and it is equal to 96. So the maximal value is this, and it gives us an important information about the lower boundary of our diagram, because we have that on the one hand, the diagram is above this line with this slope, and on the other hand, if we draw the points corresponding to rhombi, we find a segment. So we find that this segment is in the diagram, it is a lower bound, so it means that we have described explicitly a portion of the lower boundary. Okay, so the lower boundary at least in a part which is quite big. I will show you how big it is. It is linear. It is described by this function here. And the point in which we stop the description is the x-coordinate of the square. So we go from the square to a segment. So the stopping point is the square. Why this is related to a conjecture by Polya? Because this functional here has already been studied by Polya, as many other things. However, he studied also this shape functional, and this question was, what is the maximum among convex sets? Of course, he did not require the double symmetry, and this question is open. Polya's conjecture is that without symmetry assumption, the best shape should be an equilateral triangle. Of course, in this shape functional, the shape functional that Polya considered, W is the real W with respect to the center of gravity, so not the one centered in Z. So this is still an open problem that is part of our perspectives. Okay, I don't have the time to detail this part, but just to say that we have also investigated the behavior near corners. So we said that we have two extremal points in our diagram, the origin and the vertex 1, 1. And so it is interesting to look at what happens here and there, and more precisely what are the tangents of our bounding functions. And we give precise values for the slopes of these tangent lines. So I will spend my last minutes by summarizing everything we have said. So this was the starting picture. In this picture, I recalled all the questions that one addresses. And this is I will show you the final picture of the diagram. Picture in the sense that it is really obtained, it is a picture obtained by solving L plus and L minus numerically. I recall you that compute L plus and L minus amounts to minimize or maximize the perimeter when the moment of inertia and area are fixed. The picture is this one, and it confirms our theoretical results. Let me recall why. So the diagram is the region inside two increasing continuous curves. Then we have that these curves start from 0, 0, even if they are not defined as 0, 0, but they start from here, and they arrive both at 1 in 1. Moreover, we have the tangents here and tangents there are the same that we found theoretically. Then we have that optimal shapes here are C11 shapes, and this is an example of optimal shape, a sort of ellipse, but it is not an ellipse. Then we have polygons here. In this part, which is very small, it is around 0.9 something to 1, we have polygons. And then the lower boundary is a segment from 0 to the coordinate x of the square. So this is all. What remains to be studied, of course, to remove the double symmetry assumption and to address, so double symmetry assumption in general for the diagram, try to figure out what is the picture, and then, of course, address the conjecture by Polya. So what happens if one wants to maximize this quantity without the double symmetry constraint. And with that, I stop and I thank you for your attention.